Hello, I am Damian Mayorga Pen, and I'm going to tell you a little bit about my poster that bears the title Emulated Computations of Heterotic Yukawa Couplings. This is based on a series of works that have been done in collaboration with Per Berglund, Georgi Budvaya, Tristan Hupsch, Vishnu Yeyala, Challenger Mishra, and Justin Tan. Let me start by saying that Calabi-Yau compactifications of the heterotic string provide a promising route to recovering the four-dimensional particle physics described by the standard model, and that in this work, I'm going to present you with numerical computations of physical Yukawa couplings in the standard embedding and demonstrate the existence of natural hierarchies among those. While unnormalized Yukawa couplings are quasi-topological and therefore straightforward to obtain, the computation of kinetically normalized couplings is more cumbersome, and there are two reasons for that. The first has to do with the fact that the Ricci-flat Calabi-Yau metric enters the computation, and so far we do not know of its closed form for a single compact Calabi-Yau threefold. The second has to do with the construction of representatives for the matter fields as harmonic forms in suitable cohomology classes. Our claim is that both these issues can be tackled using a special type of neural networks that we call spectral networks, and that this approach leads to precise kinetically normalized coupling. Let me tell you what spectral network is. It is basically a deep neural network coupled to a spectral layer. The inputs to the network are points in the Calabi-Yau given by their coordinates in products of projective spaces. The spectral layer is an embedding that removes all possible sister actions from the ambient spaces, enabling us to obtain a globally well-defined output. If you want to obtain the flat metric, you can deform a C-scalar metric by the Jacobian of a global function. We can take that global function to be approximated by a spectral network. We have trained on many examples. One of them is the cephalopencil. This is a family of K3 surfaces given in terms of a parameter lambda. At 4 special values of lambda, the geometry becomes singular. Here in the plots, you see the Euler number of the cephalopencil computed using the machine learned metric. As you can see for smooth surfaces, the result coincides with the expected value of 24. But what about the singular ones, you might ask? Well, we observe jumps at these points, but these jumps can exactly be compensated by the curvature contribution of the number of spheres that one needs to glue to the singular geometry in order to make it smooth. We can follow a similar approach to construct harmonic representatives with spectral networks. Having both ingredients at hand, we can now compute the Yukawa couplings. Here I present you with some of the unnormalized and normalized couplings for the Cauchy-Yen metric. As you can see, normalized couplings are roughly of the same order of magnitude. But as we introduce the normalizations, we observe that for increasing values of the complex structure parameter epsilon, hierarchies of order 10 to the 2 start to develop. Finally, let me mention that we have created CIMIC, a GitHub repository that has been made available to you and enables computations of metrics, differential geometry properties associated with them, and of course, Yukawa coupling. If you'd like to know more about this work, please get in touch. I'm looking forward to seeing you at the Strings Conference.